Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore solids and semiconductor devices. On this first slide, we're just getting started, so I'll briefly introduce what we'll cover. We'll look into the fundamental properties of solids, delve into semiconductor materials, and examine key devices that make modern electronics possible. I look forward to guiding you through this fascinating topic. Let's get started. Let's explore the distinction between intrinsic and extrinsic semiconductors. Intrinsic semiconductors are pure materials, like silicon or germanium, where the electrical properties are determined entirely by the material itself. They have a balanced number of electrons and holes, which means their conductivity is quite limited at room temperature. On the other hand, extrinsic semiconductors are intentionally doped with impurities to modify their electrical properties, making them more conductive. For example, adding phosphorus or boron creates N-type or P-type semiconductors, respectively. Recognizing this difference is crucial because it helps us understand how semiconductors can be tailored for specific electronic applications. This distinction ties directly into the overall theme of how different materials behave in terms of electrical conductivity and their role in electronic devices. According to quantum mechanical laws, the energies of electrons in a free atom cannot have arbitrary values, but only some definite, quantized values. However, when an atom becomes part of a crystal, these energy levels undergo modification. Now, this modification isn't very noticeable for the inner shell electrons, which are completely filled and tightly bound. But for the outermost electrons, the story is quite different. Since these electrons are shared among many neighboring atoms, the influence of the electric field between the atomic core and the shared electrons becomes significant. This causes the energy levels to split or spread out, forming what we call energy bands. To visualize this, think of a single crystal of silicon with N atoms, each associated with a lattice site. The electronic configuration of silicon is 1s 2, 2s 2, 2p6, 3s 2, 3p2, with an atomic number of 14. These energy bands are fundamental because they determine how electrons move through the material, which ultimately affects its electrical properties. Let's take a closer look at the forbidden energy gap, which is a critical concept in understanding how electrons behave in solids. The forbidden energy gap, also known as the band gap, is the energy range where no electron states can exist. It separates the valence band, where electrons are normally present, from the conduction band, which is where electrons can move freely and contribute to electrical conductivity. Now, the valence band is filled with electrons that are tightly bound to atoms, while the conduction band is higher in energy and typically empty in insulators and semiconductors. When energy is supplied, say, through heat or light, electrons can jump from the valence band across the forbidden gap into the conduction band. This transition is fundamental because it determines whether a material behaves as an insulator, semiconductor, or conductor. The energy levels within these bands form what we call the energy band diagram, which visually represents the allowed and forbidden energy ranges. Finally, understanding how these energy bands form in solids is essential for grasping how electronic properties emerge. The overlapping of atomic orbitals in a solid leads to the formation of these continuous energy bands, rather than discrete levels like in isolated atoms. This band formation underpins the electronic behavior of materials and is key to designing electronic devices. Let's examine how the energy levels of atoms change when they come close to each other. Initially, the energy associated with the S and P levels of each atom gets slightly altered. For a single isolated atom, the S level actually splits into 2 N levels, and similarly, the P level splits into 6 N levels. Now, as the atoms get closer, specifically when the distance between them is between OB and OC, the interaction between the outermost shell electrons of neighboring silicon atoms becomes noticeable. This causes the energy levels to start splitting apart. When the atoms are at a distance equal to OC, we see that there's no visible splitting yet, but the tendency for the levels to split begins to develop. As the atoms approach closer, between OC and OD, the interaction becomes stronger, and the energy levels start to split more significantly. Finally, at a distance equal to odd or less, the energy levels are well split, and each atom's original energy levels are now overlapping and blending into a broader band. It's important to note that before the interaction becomes appreciable, each atom has its own set of sharply defined, discrete energy levels. These are identical across atoms, with the outer two subshells, 3s and 3p, containing electrons filling two ns electrons and two np electrons, respectively. All these filled levels are at the same energy initially, but as the atoms interact more strongly, these levels broaden into bands, which is fundamental to understanding the electronic properties of materials like silicon. Let's take a closer look at how energy bands work in solids. The exact shape of these bands depends on the relative orientation of atoms within the crystal structure. Now, if all the energy levels within a band are completely filled with electrons, these electrons can't really move around freely. That's because there are no vacant energy levels nearby for them to jump to. So, full bands mean the electrons are essentially stuck in place. Now picture a band of 4n filled energy levels. This band is separated from the next band, which has 4n unfilled energy levels, by a gap called the forbidden gap, or sometimes just the energy gap or band gap. The lower band, which is fully filled, is known as the valence band, and the upper unfilled band is called the conduction band. As we move to the case where the energy gap disappears completely, things change dramatically. In this situation, the 8n energy levels are distributed continuously, meaning we can only say that half of these levels, 4n, are filled and the other half are empty. Now, because n, representing the number of atoms per cubic meter, is extremely large, around 1029, and each energy level is only a few electron volts apart, the levels become very densely packed. To give you a sense of scale, the energy spacing between these levels can be as tiny as about 10^3 eV in a 1 cm3 crystal. This dense collection of closely spaced energy levels is what we call an energy band. In essence, these energy bands are fundamental to understanding the electrical properties of materials, whether they behave as insulators, conductors, or semiconductors. Let's take a closer look at the second energy band diagram. Here, we see that the conduction band overlaps with the valence band. This overlap occurs because the lowest energy levels in the conduction band are actually lower than the highest levels in the valence band. As a result, electrons from the valence band can overflow into the conduction band, making them free to move throughout the crystal and conduct electricity. Now, at absolute zero temperature, the highest energy level in the conduction band that electrons occupy is called the Fermi level. The energy associated with this level is known as the Fermi energy. When electrons gain enough energy to surpass this Fermi level, they can freely move and contribute to electrical conduction. This overlapping of bands is a key feature in metals, which explains their high electrical conductivity. Electrons can easily transition into the conduction band, allowing metals to conduct electricity efficiently. In contrast, the first diagram shows a partially filled conduction band, where only some energy levels are occupied, and a little additional energy can push electrons into higher, empty levels, enabling conduction. Understanding these energy band structures helps us grasp why different materials exhibit varied electrical properties, metals, semiconductors, insulators, and how their electrons behave within these bands. Let's take a closer look at the valence band. The energy gap here, known as the forbidden energy gap or, for example, is quite small in semiconductors. Because of this, the fraction of electrons that can jump across this gap is relatively large compared to insulators. When an electron leaves the valence band, it leaves behind an unoccupied energy level, which we call a hole. These holes behave as positive charge carriers, and their movement from one position to another is essentially a positive charge flowing through the material. Now, moving on to the conduction band. At absolute zero temperature, no electrons have enough energy to make the jump from the valence band to the conduction band, so the material acts as an insulator. But at room temperature, some valence electrons gain enough thermal energy to overcome the energy gap and move into the conduction band. Once in the conduction band, these electrons can move freely and conduct electricity, even under the influence of a weak electric field. This ability of semiconductors to switch between insulating and conducting states based on temperature and energy levels is what makes them so versatile and fundamental to modern electronics. Let's now look at the forbidden energy gap, which is a key concept in understanding insulators. As we move from the valence band, where electrons are normally present, to the conduction band, there's a significant energy difference called the energy gap. This gap is so large that, even if we heat the material, electrons in the valence band can't jump across to the conduction band easily. This large energy gap is what makes insulators poor conductors of electricity. Electrons remain tightly bound within their atoms, and very few, if any, can gain enough energy to move freely. Now, when an electron does receive enough energy to break free, it leaves behind a vacancy called a hole. These holes can move around the lattice, and electrons can jump from neighboring atoms to fill these holes, creating new holes elsewhere. But overall, because of this large energy gap, the flow of electrons, and thus conduction, is effectively blocked in insulators. That's what makes them so different from conductors and semiconductors. An intrinsic semiconductor is a pure form of semiconductor material, meaning it has no impurities added to it. In the case of silicon, or Si, the energy gap, which is the energy difference between the valence band and the conduction band, is about 1.1 electron volts. For germanium, or G, this energy gap is slightly smaller at around 0.74 electron volts. Now, in an intrinsic semiconductor, an important point to note is that the number of thermally generated electrons always equals the number of holes. This is because when an electron gets enough thermal energy to jump from the valence band to the conduction band, it leaves behind a hole in the valence band. So, for every electron that is excited into the conduction band, a corresponding hole is created. If we denote the concentration of electrons as Ni and the concentration of holes as pi, then in an intrinsic semiconductor, Ni equals pi. This mutual equality is a key characteristic. The value of Ni or pi, which is the same in this case, is called the intrinsic carrier concentration. It's an important parameter because it tells us how many charge carriers are available naturally in the material at a given temperature. Understanding this balance in intrinsic semiconductors helps us grasp the foundation before we explore how adding impurities, either donors or acceptors, leads us to extrinsic semiconductors. Now, let's look at some common methods of doping semiconductors. One approach involves bombarding the semiconductor with ions of impurity atoms. This technique uses high-energy ions to penetrate the material and introduce dopants directly into the crystal lattice. Another method is adding impurity atoms in the molten state of the semiconductor. Here, the material is heated until it melts, and then dopant atoms are mixed in thoroughly. As the crystal cools and solidifies, these impurity atoms become incorporated into the structure. A third technique involves heating the crystal in the presence of dopant atoms. In this case, the impurity atoms are introduced at high temperatures so they can diffuse into the crystal, enabling controlled doping. Now, it's important to remember that doping is essentially the deliberate addition of a very small amount of impurity into an intrinsic, or pure, semiconductor. These impurity atoms are called dopants. When a semiconductor contains these dopants, we refer to it as an impure or extrinsic semiconductor. Connecting this to the overall theme, doping is crucial because it allows us to modify the electrical properties of semiconductors, enabling a wide range of electronic devices. Whether through ion bombardment, melting, or diffusion, each method offers unique advantages for tailoring these properties to our needs. Let's take a closer look at the energy needed to detach that fifth loosely bound electron in germanium. It's surprisingly small, around 0.045 electron volts. This means that just a little bit of thermal energy, which is always present due to temperature, is enough to free that electron. Once freed, this electron is ready to conduct current through the material. Now, an interesting factor here is the force of attraction between this free electron and the positively charged impurity ion, which has a charge of +5. This attraction isn't as strong as it might seem because it's weakened by the dielectric constant of the medium. Essentially, the dielectric constant acts as a buffer, reducing the electrostatic pull and making it easier for electrons to become mobile. Moving on, when we talk about doping a group IV semiconductor like silicon or germanium, both of which are tetravalent, we introduce an impurity from group V, such as phosphorus, arsenic, or antimony. This process creates what's known as an N-type semiconductor. Specifically, if we dope germanium with arsenic, the arsenic atom, which has 5 valence electrons, bonds covalently with 4 germanium atoms using 4 of those electrons. The 5th electron, however, is loosely bound because it doesn't have a full bonding role. This 5th electron can easily be freed with a small amount of energy, contributing to electrical conductivity. In essence, this doping process introduces extra electrons into the system, enhancing the material's ability to conduct electricity, an essential aspect of how semiconductor devices function. When an intrinsic semiconductor is doped with donor impurities, something interesting happens beyond just increasing the number of electrons. Not only do the electrons go up, but the number of holes actually decreases below what you'd find in an undoped, intrinsic material. This balance between electrons and holes is key to understanding how N-type semiconductors behave. We use the symbols N and P to represent the concentrations of electrons and holes, respectively, in an N-type semiconductor. An important relationship here is that the product of these two, Np, equals Ni squared, where Ni is the intrinsic carrier concentration. Similarly, for holes, pi equals Ni squared as well. This means that as we increase the number of electrons with doping, the number of holes must decrease to keep that product constant. It's a fundamental concept because it shows how doping shifts the equilibrium between electrons and holes, which directly impacts the electrical properties of the material. So, in the context of our overall discussion, understanding how doping affects carrier concentrations helps us design better semiconductors for various electronic applications. It's all about controlling these carrier populations to optimize device performance. In a p-type semiconductor, the majority charge carriers are holes, while electrons are the minority. It can be shown that the product of the electron and hole concentrations, Np, equals the square of the intrinsic carrier concentration, Ni squared. Similarly, for holes and electrons, pi equals Ni squared. Now, when we talk about group IV elements like silicon or germanium, which are tetravalent, they have 4 valence electrons. Doping them with a trivalent impurity such as indium, boron, or gallium creates a p-type semiconductor. Let's take germanium doped with indium as an example. Indium has 3 valence electrons. When it substitutes a germanium atom, the 3 valence electrons form covalent bonds with 3 neighboring germanium atoms. However, the 4th bond can't be completed because indium only has 3 electrons, leaving a vacancy. This vacancy, or missing electron, is what we call a hole. It acts as a positive charge carrier in the material. Essentially, doping introduces these holes, which become the primary carriers of positive charge, enabling the semiconductor to conduct electricity in a controlled way. So, in summary, doping with a trivalent element creates holes by creating these vacancies, making the material p-type, with holes as the majority carriers. And this concept is fundamental to how semiconductors are engineered for various electronic devices. Let's take a closer look at the distinction between intrinsic and extrinsic semiconductors. Starting with intrinsic semiconductors, these are essentially pure group IV elements, like silicon or germanium, with no impurities added. Because they are pure, their conductivity is quite limited and tends to increase slightly as the temperature rises. This is because higher temperatures generate more charge carriers within the material itself. Now, moving on to extrinsic semiconductors, these are created by intentionally introducing impurities, elements from group III or group V, into the base material. This doping process significantly enhances conductivity, making extrinsic semiconductors much more efficient. In fact, their conductivity depends heavily on the amount of impurity added, not just temperature. An important concept here is the behavior of charge carriers. In intrinsic semiconductors, the number of holes is always equal to the number of free electrons, maintaining a balance. However, in extrinsic types, this balance shifts. In N-type semiconductors, where extra electrons are introduced, the number of electrons exceeds the holes. Conversely, in P-type semiconductors, holes are more numerous than electrons. By understanding these differences, we see how the manipulation of impurities allows us to tailor the electrical properties of semiconductors to fit various applications, which is fundamental to our overall discussion on semiconductor devices. Let's now look at the key differences between semiconductors and metals. First, at absolute zero temperature, or 0 Kelvin, semiconductors act like insulators, meaning they don't conduct electricity well. But as the temperature rises, their conductivity actually increases, which is quite the opposite of what we see with metals. In contrast, metals have a different behavior. Their conductivity decreases as the temperature goes up, mainly because higher temperatures cause more lattice vibrations, which scatter electrons more and hinder current flow. Next, when we apply a potential difference or voltage, the conductivity of semiconductors increases. This is due to the fact that more charge carriers are generated or become mobile with higher voltage. However, in metals, conductivity is an intrinsic property. It's largely determined by the metal's own structure and isn't significantly affected by the applied voltage. Another important point is how these materials obey Ohm's law. Metals generally obey Ohm's law quite well, meaning their current is proportional to the applied voltage. Semiconductors, on the other hand, only partially obey Ohm's law, especially because their conductivity can vary with temperature and doping. Speaking of doping, adding impurities to semiconductors can dramatically increase their conductivity. This is a fundamental principle behind semiconductor devices. But in metals, if you make alloys by mixing different metals, the conductivity usually decreases because of increased scattering and imperfections. So these differences highlight how semiconductors and metals are fundamentally different in their electrical behavior, which ties back to our overall discussion of material properties and their applications in electronic devices. Let's take a closer look at the charge and hole concentration in semiconductors. When the applied electric field is small, the semiconductor behaves according to Ohm's law, meaning the current is directly proportional to the voltage. In this context, it's important to note that electron mobility is higher than hole mobility, which influences how easily each charge carrier can move through the material. Also, mobility tends to depend only weakly on temperature, so temperature changes don't drastically alter conductivity in this regime. Now, considering the current density, it can be expressed as a combination of contributions from electrons and holes. The equation I equals E of VE plus NHEA captures this, where Ne and NH are the electron and hole concentrations, E is the charge of an electron, O is the cross-sectional area, and are their respective drift velocities. Moving on to resistivity, we can relate it to these quantities as well. The electric field, E, can be written as E equals E VE plus VH, which essentially links the electric field to the sum of the current contributions from both types of carriers. Finally, these relationships form the foundation for understanding the electrical conductivity of semiconductors. They show how the movement of electrons and holes under an electric field determines how well a material conducts electricity. And this understanding is crucial for designing and analyzing semiconductor devices.